Colloquium. Today is November 17, 2022. We are really honored to have a special guest to give a speech. And before I talk about our colloquium topic, and I'll let Professor Peter Pan talk about to introduce to you today's colloquium. Dr. Pan?
Yeah, thank you, Carl. Good evening, all the guests from the U.S., and good morning for all the guests to all the guests from Taiwan. And welcome to our this colloquium today. Just give me a couple of minutes, just 1 minute, a few seconds to give you a short, brief introduction to DAC. The Data Analytics Colloquium. We started this colloquium, an online seminar 3 years ago, and this is our 3rd year. And I'm fortunate and privileged to have this program to keep going. And it's supported by National Chongqing University and as well as University of Texas at Dallas, School of Economic, Political, and Policy Sciences. So we try, and then we do try very hard, and then we have done a good job. So to convene well-known international scholars and the data scientists. So in this seminars or workshops, so we can discuss and exchange the most up-to-date the methods into science. Data and analytics. So today we have a very special guest, Professor Patrick Brandt, and then I will just turn the microphone to Professor Ho, and then to give a brief introduction. Carl?
Hello, hi, thank you. And let me see my camera. My camera's been working somehow. It's not showing on the screen. But anyways, allow me to introduce Professor Patrick Brandt, and a colleague we've known for over a decade. And Dr. Patrick Brandt is the Professor of Public Policy and Political Economy and Political Science in the School of Economic Policy, Political and Policy Sciences at the University of Texas at Dallas. And his research employs time series analysis methods and machine learning in a variety of areas. The main time series models employed in his research involve Bayesian statistics and multiple equations or vector autoregression models, and methods for producing, evaluating the quality of forecast, the derivation of new models for time series of counts, and modeling structural change and endogenous shift in data over time. And I want to add a few more footnotes about Dr. Brandt. He's quite well-known political methodologist, and I think he's one of the early methodologists that found a few efforts in political methodology, including the conference and also the journal Political Analysis. And all these efforts, and he started early, and he's basically like one of the founding fathers and of political methodology, the movement. And now he is also recipient of multiple grants, and also most well known is his National Science Foundation grant that's setting up efforts and servers to deliver the real-time political event data. And I think I should let him to talk more. And without further ado, allow me to introduce Professor Patrick Brandt.
Thanks, Carl, and thank you to you, Peter, as well, for the introduction and the chance to do this. This is something I've kind of come back and forth to at various points in doing research, and I realized in another project I was doing that this became more timely again. So I've circled back and taken something that I'd done a bunch of work on over a decade ago about how to model changes in data over time, and kind of looked back and said, well, what's going on in this area now? And how can we use and employ these models to think about different questions in policy analysis or policy interventions or causal inference and things like that? I can go further on those points, but let me start off by situating this. What's great here is there's a couple of recent well done review articles that are really actually quite accessible, despite their not being written originally for a social science audience. One is this paper by Au and Horth, and the other is this paper by Jewell and his co-authors just this year in the Journal of the Royal Statistical Society. And I've given you the links for them there so you can get to them. They provide nice reviews of kind of what's the state of the art in this. And it's kind of important to lay that out here because this is an area where some people are looking at these problems from the side of machine learning. Other people are doing it from time series analysis. Other people are doing it from basic statistics. And the underlying problem is you observe one set of data, usually indexed by time or geography or some ordering principle. And there's some change in it when you cross over some border or some barrier in time. It could be an intervention of something that happens. It could be you cross geographically from one location across a boundary into another location, and things change either how they're measured or what's measured or to be evaluated. And a lot of times what we want to do is have some sort of model that says, well, is there a statistically significant difference in those groupings over time, over space, something like that? This seems a really straightforward thing. You're like, well, this just sounds like a simple t-test difference of means, except for the fact you have that underlying structure. And that really complicates things. The Jewell paper does a nice job of laying this out. Basically, as you get right up to the point where things are going to change, you wouldn't want to say the data are necessarily independent because the ones near the point at which it changes are somehow different than the ones when the change occurs and what happens after on the other side of the boundary. And so they break this up and they think of different methods for finding where these boundaries or these change points are. And in the Jewell paper, they focus on what I call the type 1 and type 2 models here, binary segmentation and regularization models. I almost back up though, because I think of the way we normally teach this. We teach what we call kind of what I call, just since it's earlier, I call it type 0. Which are basic intervention or causal inference models. So you observe some point and there's a change usually known by the analyst, right? So you could have, say you have data on municipal trash collection and suddenly you institute a recycling program at a given time period. And you've observed data on the trash collection and then you implement the recycling program and you expect there's going to be some change in the trash collected. You figure it's going to go down because people are going to divert part of their waste to the recycling. And you then want to say, well, what's the impact of the recycling program on the overall refuse that's disposed of? And that presupposes that you know the intervention and you know when it occurs. Which as a policy analyst, you might think you know, but I'll show you an example here where you may not. So you could back up from this problem and say, well, I don't know when and how the break is, but I just want to look for the possibility it could be there. I want to know, is the next observation like the ones I've already seen, or is this one different? Right, so this is all the problem we're facing in teaching classes right now, right? We've taught classes for years, or we've interacted with students for years. The pandemic has occurred and we'd like to know, is there something different in the ones after? And you're asking that immediate thing in the next group after, comparing them to the prior groups. Typically, we find that by a method known as binary segmentation. So we think about how do we cut up our samples into different subsamples of data and ask whether they're different or the same from each other. Right, so this is what's known as a monitoring model. The nice thing is they're relatively easy to implement. They're hard to do inference on them. Your other option, which Jewell and his co-authors talk about, are the regularization or lasso methods. So here you take a really big data set and you'd ask, well, what's the optimal number of breaks and where do these occur? Right, so this is typically the big data approach to this problem, where you have a huge or long set of data or time series over space, over time, and you want to then find where are all the possible optimal dates and what inferences could you make around those? That's much, much harder to do, especially if a priori you don't have any idea where they are or how many there are. So we'll look at approaches that admit that or allow for that around different regularization methods. These are basically going to be sparse regression methods where we say, look, we'll let you propose a new break or a new date, but it's probably going to come with some cost to you. Lastly, we could look at Bayesian models. I have some slides and things in here. I'm not really going to do that today, but I put it in there because I think it kind of rounds out the discussion. There you have to build a full probability model about what the different breaks are. Okay, so let's take the simplest one. So I have some basic time series I want to observe y at time t. So that's the y sub t. It depends on its past through a parameter alpha. And we have some intervention or some change, right, which is our xt variable that tells us this is when we had or we observed the possible intervention or change in the time series. So if delta is positive, we think y went up. If delta is negative, we think it went down. And the idea here is your left-hand side of your dependent variable depends on its past, right? That's the yt minus 1 term that we have here. And then we have the intervention. So if you think about this setting up your data, you'd have something like the data table at the bottom right, right? You'd observe a whole bunch of y's, they'd be in one column. You'd observe a set of x's. They'd be zeros for a while, then eventually they'd turn from zeros into ones. And those would just measure, okay, I didn't see the new recycling program. And then at this point forward, I observe the new recycling program in my trash data. And if you were putting this in a causal inference framework, you'd be saying, okay, I want to know what's the expected value of y given x is 1 versus when x is 0. And in this dynamic model, that estimate would be delta divided by 1 minus alpha. That'd be the total effect of the intervention, accounting for how much yesterday's value feeds through and affects today's. So that's kind of our simplest one. You know when it is, and you know when the intervention variable goes from 0 to 1. So this is like the most straightforward kind of policy analysis thing you could do, right? Is, you know, you're answering for a political expert or a government official or somebody else. Does this change or does this thing we do make any difference whatsoever for public policy or political outcomes? So the idea here is you just would fit a regression or an autoregressive integrated moving average time series model. You'd use a Box-Jenkins type inference engine there to say what's the effect of the intervention. You could cast it differently and treat it as a problem of causal inference and pull out all the average treatment effect modeling technology that you'd learn in that sort of stuff. So in some sense, this is the easy case. This is basic, you know, data analysis where you specify a given intervention variable. Let's think about where this could go wrong, though. And here I'm going to give you kind of one classic example from a paper by Harvey and Durbin. And they wanted to look at the change in the number of traffic fatalities that came after seatbelt laws were required, basically requiring people to wear seatbelts in Britain. And so their dependent variable is the one at the very top, right? It's what they call the working time series. And it's the number of motor vehicle deaths or casualties in the UK. And it's been transformed with a log base 10 transformation. And you see, looking at that, there's a seasonality to it. It's higher in some months, lower in others. The seasonal pattern seems to repeat. It basically repeats, you know, in the summertime months, right? In the summertime, more people are out driving. There's more exposure to automobiles. Thus, there's more road fatalities. The bottom two graphs show the correlation and the partial autocorrelation plots or those over time. So the ones that are centered over where the x-axis says 1, that's the effect 12 months out, right? So you see that's representing the seasonality that's there. And then the partial effect is shown in the very bottom one. So ideally what they want to show is, well, what's the causal intervention effect? That is, take the data for this period through the mid-1980s, use that and estimate, well, what would we expect traffic fatalities or traffic casualties to be, road casualties to be, prior to instituting the seatbelt law and the requirement that people had to wear seatbelts, versus what is it actually after? Measure that gap in between and say, well, that's the causal effect, and that's what we get from having people wear seatbelts. And if you do that, you'll get a model that looks like this one here on the next chart. And I've drawn in here the original series in the black to the left-hand side. And then in the right, there's two sets of things included. One of them is a thin red line, which is the forecasted effect prior to the intervention, right? The intervention period is this lattermost period in the mid 1980s, up through late 1985. And a 95% credible intervals in blue. Now, here's the problem, is if we just do that, and we say we knew when the intervention was, the forecasted data series overlaps with, and its confidence interval overlaps with the actual observed data, right? The bottom edge of that blue line encompasses part of the data that we actually observe. So the implementation of the seatbelt law probably isn't a statistically significant predictor of the decline in the number of traffic casualties. And it begs this other problem of, when we're looking at these sort of change point or intervention models, a lot of our specification comes down to, well, what other possible regressors or causal explanations could there have been for this to happen? Could it have just been the natural history, or, I only observed the road casualty data over a certain subsample of data, and if I'd observed it over a longer period of time or a different period of time, I might have seen something different. Alternatively, it could be that I'm missing an independent variable that needs to be included in this model that would possibly explain that. So my next slide actually looks at this and says, okay, well, let me look at the effect of trying to predict the traffic casualties based on their past. That's these autoregressive components I've included here. Right, so we fit an autoregressive integrated moving average model with one lag of the dependent variable. So we've asked, how does last month's number of casualties predict this month? Then we've asked how much 12 months back does. So it's a seasonal lag. That's these first two coefficients here. So those are the alpha coefficients, like I was mentioning in that earlier original equation. We've included an intercept. Then we've got a measure of the total miles traveled. Then we have petroleum prices. And they're negatively related, as you'd expect. The more gas prices go up, the less road fatalities there are, because there's fewer people driving. And then we have the effect of the law, right? The change in requiring seatbelts. Well, now that's marked here with this little black box. And you see here, the decline from the seatbelts is much, much smaller than what was on the earlier plot on the last slide, right? It's basically saying you have about a 10% decline in the casualties. Most of the effect, over 100% of it actually, is due to the change in the petroleum prices. And I plotted the petroleum price over here on the right. And you see what happens. Well, the petroleum prices go way, way up during the same period at which you're looking for the intervention. So you're left with this issue of you have multiple possible causes. It could be the oil price changes. It could be the change in public policy. So we need to have models that can rule in or rule out these different possibilities and allow for these to be part of our explanation for, well, how big of a change did we really have? Is it just a change that's due to some intervention or not? And how much do I actually have to know about my data to do this? Here it becomes really obvious because we know something about this really volatile period of oil prices in the 1970s and 1980s. So that's an obvious confounder. Let me give you one that's a little more subtle. This comes from a paper with Charlene Martens, the Nerdhood, and some other co-authors that I did. And we got into looking at this data, some of which is rare events, some of which is not, on disease burdens for basically foodborne illnesses in Belgium. There's a long background story on how this came about. That basically about 5-6 years ago, I was approached by this group and they asked me to do some analysis with them. So they happen to have data on this. And what they really wanted to get at was, what's the total life burden of these illnesses? Right, the actual number of deaths from Salmonella, Campylobacter, or Listeria in a country like Belgium are actually quite small. But what they do is they really impact people's disability-adjusted life years. That is, they make it hard for people to work or make them suffer longer from other illnesses or things like that. So while you may not have a big death burden as a result of these diseases, you have a lot of time lost from work, a lot of societal costs that come from these foodborne illnesses. And they gave me the data and I started analyzing it for some of these. And I noticed immediately that there were some odd changes in this. And I said, well, what's happening and why are the data changing? And I'll show you the data slide here in a minute. And they said, well, the data are changing because, we're requiring that certain animals and certain things be given vaccinations to prevent their ability to contract and spread these foodborne illnesses. And I said, well, when was that? They said 2005. And I said, well, that's nice, but that doesn't fit the data. So here's the data on the Salmonella cases. Right? So these are monthly cases of Salmonella in Belgium over an 11-year period. And you see here, the drop starts prior to 2005, right? Because we have this seasonality here in these different classifications of Salmonella cases. And I started pestering them and they said, well, no, the change comes in 2005. You should just put in a control variable for post-2005, because that's when everyone knows the European Union required this vaccination program to be instituted on, highlighted it here in bold, breeder poultry flock. These are basically the chickens that are bred to then give birth to the other chickens that you eat. So there's one set of farmers who raise the breeder stock, they sell them off to the other chicken farmers who then have their chickens lay the eggs, and those are the ones that grow up to be the chickens that you get to eat when you eat chicken. Yeah, so I got to learn a lot about how chickens are raised in Belgium as a result of this. It's amazing. You start asking where the data come from, and you learn all sorts of things you probably didn't want to know. There's chicken farmers for chicken farmers is basically what I learned. And I said, well, why does this happen before 2003? And they went, and one of the scientists asked one of the chicken farmers who asked the chicken farmer, or the chicken farmer's chicken farmer, what was going on here? And he said, well, yeah, he goes, well, we knew we had to provide these chickens that had been vaccinated. And they told us that if we provided chickens that weren't properly vaccinated and the chickens came down with Salmonella, they were going to cull the entire herd, meaning they were going to kill the entire flock. And so they go, well, we don't want to bear that cost. and we don't want our clients don't want to buy birds where they run that risk. And so what did they do? They just started vaccinating early. So 2 years prior, you had this kind of pre-intervention effect. So here you thought you knew when the intervention was, when really people go, well, I'm going to have to do this anyway. So I'm just going to adopt the policy even before the policy deadline because it's relatively low cost. Well, that has other implications if you're trying to estimate, well, what's the cost of the disease burden? Because the disease burden started dropping prior to when you expected it to, right? So you're going to incorrectly estimate the total amount of disease and its decline or changes, which means then you're going to misestimate the total cost of the disease burden. So, I mean, like getting the timing right really matters here on these things. I like this one because it's kind of a neat public policy example and we can kind of conceive around it, but there's other ones that come up with this in terms of like energy use policy, in terms of how do you mix up using gas powered plants versus coal powered plants versus wind power and things like that, and the relative costs of turning them off and on that fit this same sort of thing. So these are all the things that can go wrong, right? You may not know the intervention point, or you get it wrong, or you're missing an independent variable. And so you're just getting these potentially really badly biased inferences coming out of this thing. On top of which, when you take data like these examples I've shown you, and you try and test for parameter stability or stationarity in them to know, well, what's the right dynamic model I should be fitting for this? That is, how many past values do I need to actually go into this thing? A lot of times you're going to get it wrong if you haven't accounted for the change points right. And this is a result from Madala and Kim that goes back almost 30 years at this point. So we really want to look at, like, how do we think about doing this? So one way is binary segmentation. And it turns out the literature on this actually dates back 60, 70 years at this point. And it comes out of statistical control theory. Like, you're basically trying to figure out, okay, I have something being produced on an assembly line. What's the chance the next thing coming through the assembly line is defective? Right? And I need to detect that there's been some breakdown that may be creating defective product coming off the end of this thing. And so we've got lots of techniques that have been developed for this, right? If you've ever seen a cumulative sum of squares test or a Chow F-test, they're all versions of this. Bay and Perrone, about 25 years ago, came up with some other techniques that extend this and do it in kind of a linear regression framework, which is what I'm going to show you here. The idea here is I have some dependent variable explained by some independent variables, and the effect or the parameters of those independent variables changes. And we want to detect, does that parameter change? So I don't have to know what the intervention is or the interaction of any intervention with the covariate. I just have to know the regression relationship changed somehow. It could have gone from it was significant to it was zero. It could have gone from it was a positive effect to it was a negative effect. Right? All those are possible here. So we want to look at the basic setup for this from Bay and Perrone and realize that what's going to happen is we're just going to take our sample of data and split it at some observation. Here we're going to organize the observations by time. But what's going to happen is, like in the salmonella example, is at some point in time, I'm going to say there's some split. And the relationship after that point in time is different than what it was before that point in time. The interesting one here is the authors realized this is similar to a linear programming problem, And they're doing this right at the point everybody's finally starting to get multi-core processors in their computers. And so they take what had been up to that point kind of a brute force, kind of ugly, almost supercomputer problem, and made it something we could all do on our laptops. Which kind of opens up the possibility for doing what I'm going to show you here. So here's their basic setup, which is you have a regression, your dependent variables y, your independent variables x. So the x here always has the same effect on y through the coefficients beta. But there's some other covariate z that has an effect that changes, and its different coefficients are delta j. And these j's are going to define out the index for how many subsamples or subgroupings of the data you could have. And you can have up to m plus one of them. So if you think about it, if I have one break, I have two subsamples. I have one before and one after. Right? So when m is one, I have m plus two groupings. That then means I can have time indices at t sub 1 and t sub m that tell me when those changes occur, right? So then think about when m is 2, that means I have 3 separate subsamples, right? And I have 2 breaks that I have to define. But you have to keep straight in your head, the number of breaks are the number of samples. That's the thing that confuses students when they see this. You have to keep that in mind.
But also,
so the idea here is, sorry, what's that, Carl?
All the covariates are doing contemporary.
Correct. Yeah, right now, yes.
Then you
so
got the Z to estimate the different regions.
Yeah, that's exactly it.
Yeah,
so
that's right.
If you knew the interventions, you'd just say, oh, I know Z is a vector of zeros and ones, and I just want to find what the one delta is that tells me the difference between the group that's 0 and the group that's 1.
Yeah.
So they write this problem out and they realize it's the same as the usual least squares problem. Minimize the sum of squared errors, right? So I have yt minus the prediction of the x's times beta minus the prediction of the z's and the deltas. But now I just have to find that sum of squared errors over all the different possible splits of the subsamples. So I have to say, okay, I have these, if I had 2 interventions or 2 breakpoints, I could have them here, I could have them here, I could have them here, I could have them there, I can have them there, right? I have to think about all the combinations I could have those 2.
Yeah.
And then you start going, that's a lot of regressions, Dr. Brandt. Yes, it is a lot of regressions to have to do. So we've got to figure out, well, what's that optimal set of splits? And those are going to be the ones we're going to call these t-hats, t-hat 1 through t-hat m. They're going to minimize the sum of squared errors. Now, realize you're going to pay a penalty for this because every time you just add another break, you basically give every observation its own unique regression or subsample of regressions. The fit's always going to get better. So we're going to have to use some penalized method that says, okay, the fit got better, but it really didn't get that much better. So practically that suggests something. One is there's got to be kind of a minimum length to these subsequences. And the norm is to say, at least in most of the software I've seen for this, it says, make it about 10% of the data. And you can figure out, and I'll show you an example here where we kind of vary that and think about it some different ways.
Then you have a sizable sample, though.
What's that?
You need to have a sizable. You need to have a sizable sample and a lot of time points.
Well, what are you going to say is sizable? If I showed you it works with 100 observations, are you willing to try it?
But how many M's?
And that's exactly it. And we're gonna see that here at some of the examples I'm going to show you.
I can tell you're going to talk about it. Yeah.
Yeah. When M is 2, It's an easy problem. It's just a grid. You just keep moving where the one change point is. When m is greater than 2, then it gets expensive, and that's where the Bay and Perron algorithm works out really nicely for this. What's nice about it also is it works off the shelf. There's implementations of it for Stata. There's implementations of it for R. My guess is there's one for Python as well. So this is something that's very accessible to do. It's not one of these boutique things. You can go just grab this off the shelf, drop your data into it, and go. And this is the key part. They've worked out the test statistics. Now, part of that is, in some ways, this is the simplest case. It's a linear regression where I'm splitting the sample. So here's the simple one. This answers part of your question, Carl, about how much data do I need for this. So here I've got 200 observations, and I made it really obvious. I did this on purpose. Is the first, 50 some observations have a mean of 0 and a variance of 1. The second, 100 have a mean of 2 and a variance of a half. And the last ones have a mean of -1 and a variance of 2. So they're really pretty distinct from each other. I mean, if you think about it, the means are either really far apart, or if the means aren't that far apart, the variances are very different. So there's a very distinct shift in the distributions going on here. What's nice is if you look at the Bay and Perron one, they walk you through how to do this. You can fit this and you can play around with those options that you'd think of. How much of a sample do I need? How big do I need the differences in the distributions to be? The example code I gave you, Carl, you can share on this one later with people in R. It lets you see what happens when you play around with these. And you'll come back, you'll have breaks. The default here, you find you have a break at observation 50 and 152. So it's very much picking up what the actual values are on those breaks. So let's jump forward one step and see one that's a little more complicated. It's also a little more timely. So here's a model of data we want to consider. The data are US industrial production. This one's going to depend a lot on what the sample is. So the original analysis for this comes from a paper by Huerta and co-authors in 2003. So if you think about it, and they're doing this in 2003, their data stop and they don't include these last set of dips. So it doesn't include the 2008 financial crisis. It doesn't include the pandemic. Right. So you have to kind of, I tell people when they do this one, when I teach it in class, I always walk up to the board and I obscure the entire thing on the right-hand side. And you look at it and you go, oh, yeah, maybe there's an underlying trend in there. And we want to know how far did we deviate from trend. Right. That's the thing the economist or a macro forecaster or somebody who cared about industrial production and growth would want to know. Is what kind of trend do we have there and how much have we deviated from it? You look at it now and you're like, we're never going to get back to that trend. And you'll see here by how we pick the sample, it affects what we say about these. So the Huerta paper is actually really complicated. They care about whether you have trend or different stationarity, and they want to use a mixture model to see if you go back and forth from one of these representations to another one. And computationally, you can work out how to do their model. It's just, even in 2022, it's a computationally expensive model to fit. I mean, it's just to write the code for it, because there's no standard kind of off-the-shelf thing for it. It's doable. I've actually got the textbook I took this example from sitting on the floor here next to me. But it's not trivial. Alternatively, you could say, look, if I'm going to weigh this out of what this should be, I want to know, well, is it stochastic or is it deterministic? If it's stochastic, then these phi terms, the phi sub 0 and the phi sub 1 here, will differ versus what's the value of beta. Right, so if phi sub 1 is 0 and beta is 0, then the whole thing is difference stationary. Meaning you would just model the first differences in industrial production and model their growth, and that would be as good a time series model or as good a predictor as you ever could come up with. You would just use long-term past growth to predict the growth in industrial production going forward. But if it's not that, then you have this changing pattern of trends. And so you'd like to know, well, is it maybe the leftmost set of things here, the phi naught and the phi 1, that's describing what's going on, and beta is 0? Or are there other times when beta is non-zero, but the phis are 0? Right? In one world, everything's stochastic. The other world, everything's deterministic. And so this is what I refer to as me picking on economists, because you get what I would call the freshwater versus saltwater economists, which is the American designation of, are you an economist at a university on an ocean, meaning the East Coast or West Coast? Or are you an economist in the middle of the United States near a lake where they're freshwater? And they tend to have differing views about the role of technology and the role of dynamics in things like economic growth. And so this lets you kind of arbiter among them. So I can put this into that Bay and Perron setup and say, well, let me do a linear regression on this. So here's the result of doing a linear regression in R. So I've regressed the first differences in industrial production on their logarithms or on their lag values. So that's the L DIIP and a time trend. And if I look down here, the differences, so this would be the phi naught, are 0.23, and they're statistically significant. The time trend is 0.0039, and it's not statistically significant. So I would go, oh, this is a stochastic model, right? It fits that approach to thinking about it as this stochastic random variable. It's going to be something I have to learn from, and I can't just say it's a fixed function of time and population. That assumes the same regression parameters from 1947 all the way through the end of the data sample. And I go, well, I don't know that I want to believe that. Maybe the parameters change. So I say, well, how many change points do I have? Right? So normally I would have done this and had the graph on the right-hand side here, where I've estimated out the residual sum of squares. That's the blue downward trending line here. And you see what you'd expect, right? As I add more breakpoints, right, I go from 0 to 2 to 4 to 10, the fit always gets better. Well, to account for the fit getting better, but I'm adding more parameters every time, I can find a Bayesian information criteria, which is fit the model, but penalize for the fact that I'm going to let it fit better by letting more and more observations have their own separate regressions. So I want to minimize the Bayesian information criteria, and I see that happens when it's 4 breakpoints, right? Because this black line minimizes out of 4. What's nice about this is this just falls right out. You fit the model, it automatically comes back and tells you this is how many breakpoints you have. You tell it, plot it for me, and it gives you this picture. But if I change the sample, right? So I know this because I used to teach this example, and I taught it the last time with data through 2016, and I got a picture like this. And so I think a few students from my time series class are on here. They probably saw the earlier version of this. I went back to reproduce it, and I added in all the pandemic data, the post-2016 data, and I get the plot on the left-hand side. And the plot on the left-hand side says there's no breaks, right? Because look at here, the Bayesian information criteria is minimized at 0. And, you know, that would tell me I shouldn't have any breaks in it whatsoever. So now I should be back to the model I showed you on the last slide. So notice some of this and whether you find breaks is, are you expecting them? But then also it's, well, what did you have for your sample? Right? If you don't have enough data that looks like what you think the world looks like before the break, you may or may not find changes after. Alternatively, if you haven't had enough time period happen after the break, you can't detect whether the data are any different after that. All right, so that factors into how we have to think about these sorts of things. So here's the result with that for the data through 2016. You see we get 4 breaks. There's the dates. They're all relatively recent. And you notice these models, when they try different numbers of breaks, most of them settle in on ones that are these more recent ones, these post-1998 ones. The bottom part of the table here reproduces what you saw in the plot. Here's the regression output for the different segments. So we get, and we see there's different constants or different drift terms. You have different lag coefficients. That's what these ones are in here that I pointed to with the second arrow. And then changes in the time trend. And so you see the world works very differently over those different subintervals. So saying you have one model that explains how industrial production works all the way through this big, long historic path is probably wrong. And it's very dependent on the data you've used to put into it and the possibility you've allowed of a parameter change. So here's the plot of that. So you can see here, I've plotted it in differences. And you see, for the most part, it's relatively the same up through 1998. And it's this period after 1998 where you see the real big changes in the regimes. And I've delineated those off here with kind of vertical dash bars to show you when those are coming in there. So here's the type 2 models. This is kind of the more recent thing. Let me see, do we have any questions or anything at that point before I make this transition?
Any questions from Taiwan side?
No, we're good.
I do have, yeah, go ahead.
No, we're
So
good here.
Here we switch and we go, okay, we want to ask now about, well, what's the trade-off in classifying a possible set of interventions against a possible set of covariates? So if you think about this, this is now saying, okay.
There's a question, Patrick.
What's that?
A question from Victor. And when you teach your class in the next couple of years, is Ely, Bai, and Perot will find a break. BP has issues. Finding break at end of samples. Oh, that's good. And you read the question?
At the end. Yeah, he's saying at the end, and that's true. Because it comes down to how much data do you allow here at the end on this. And that's actually something, I'm not really talking about it here, but it is something I looked at because that was immediately what I did when I got this set of results for the number of change points. Was I said, well, how sensitive is this to me changing how close I allow the data to get to the end versus requiring more data to be able to declare the last one? And no matter what I tried, I couldn't change the plot on the left. That is, allowing more or fewer break or more or fewer data to go in didn't make it any more or less likely that I picked up a break. And I took that to basically mean we don't have enough data there to differentiate whether or not those things are really that different, or it's just changed our historical view about whether or not any of the earlier ones are there. Yeah, see, Vic's now saying, yep. Yeah, he's definitely right there. Okay. So the other are these ones where now I have to worry about misclassification, right? So the other ones are mainly about, can I detect in the first place, right? So they're all basically about type 2 error. And the regularization model say, well, wait a minute, I have to worry about the alternatives, right? So I have to worry about type 1 error as well in making these classifications. And I've got to have some cost function for the misclassification for doing that. And it's not a really elaborate time series problem. It's literally like, I have a pile of data with one mean, I have another pile of data with another mean. How do I really know the means are that different from each other if I only observed a fraction of the data out of each pile? And then realize, well, the piles may not be that distinct from each other. Like there may be some overlap in the piles. and it gets a little more complicated because then you have to say, well, did I really have two piles in the first place, or did I actually have three? Or did I actually just have one? So there's two ways to think about this. One is the iterative approach where I look one change point at a time and then I split down within those change points, right? So that's the Bay and Perron approach. The other is this kind of burgeoning literature that's come up, and you can tell from the citation dates and things on this, it's really something that's taken off in the last few years. And I think it's taken off because of all the emphasis and people looking at big data, which is people building off of this idea from Tibshirani on lasso models and using penalized regressions to go back through and say, okay, if I'm going to add another breakpoint or I'm going to add another subsequence of data, then I've got to add another possibility for that and for the observations that go with that. Now, we got a trade-off that's going on there in how I do that. So one way to think about this in this literature is, instead of just adding another covariate that has a time-based effect, I could add a lasso. So here I have potentially a new set of regressors, or I have up to P regressors. So Y depends on some covariates and their slopes, beta sub J. And how many of them do I have? Well, I have up to P. So I've taken that sum from J is 1 to P. And I'm going to minimize the sum of squared errors around the epsilon i's. But I'm going to do it with two possible penalty functions. And the fused lasso says I'm going to have two of these. One of them is going to be about the absolute value of the coefficients. That's going to ensure that I don't add too many new variables or too many new coefficients to the model. You can add them, but they really better do something, is what it's asking. Then it's saying, okay, the ones you add have to do something a lot more than the one you already had. Meaning, if you already had a variable in there by itself, you're really going to have to show me that it has a really big nonlinear effect to add its squares. Right? That's what the second one's saying is, look, the effect of the second order part of it, or adding the jth covariate over and above the ones you already had, really has to matter too. So there's two parts going on in this. One is the overall sparseness, and then the fact that you can't just add covariates for the sake of adding covariates. They actually have to add something new compared to the ones that are there. This is getting around kind of what I refer to as the medical feature problem, right? Which is, I measure whether or not you have some marker of disease as your dependent variable, right? You have high blood pressure, you have high glucose levels, you're diagnosed as diabetic or something else. Then I have a gazillion covariates I've captured about you, all your blood chemistry, your weights, your gender, your diet. Like, I mean, start thinking about the features you can get. The number of columns of data is massive. But really, once I know a small subset of those, I probably know all the other ones too. You know, and I probably only have to know the most proximate ones. I don't need to know what was your blood glucose, you know, 6 years ago, even though the doctor probably has it. And this gets around that of trying to limit those. So Jewel and co-authors say, well, let's use this in a change point setup. And they just ask, okay, well, do I have different means? And do these means, instead of varying over periods t, they vary over periods tau? And those are going to be the true change points. And they're going to say, okay, look, we're going to declare that you have a change point here if the cost of including that change point is such that it makes the fit that much better. That is, we're minimizing your cost function, where the cost is going to be the trade-off in how much better you fit, subject to the penalty terms. Because you basically have to always have to pay the penalty to be able to include the covariate for the change point, or to include the information about the change point. So the idea in this is building off of the lasso thing. And the nice thing here is the lasso models will become computationally really cheap to do too. That was something that used to take specialized hardware and computers and a lot of time and the rest of it like 10, 15 years ago. And now it's become, you know, it's basically what's driving all the model selection in most of the modern machine learning right now. It's some version of these lasso models.
We have a question,
Carl.
Patrick. Raku has a question. Would you agree that the difference between the binary method and lasso is the additional conditionalities in lasso?
My basic reaction to that is yes, but now that I think about it, I haven't seen a good mathematical comparison of those structures against each other. I'd have to think some more. I can think of some geometric ones that I've seen for the lasso models, and I'm just trying to think through the geometry on the binary segmentation one. I have to think a little more about that. My gut says yes, but I'd have to think about it some more. So back on that one, here's just another example where, again, we've kept that same sort of structure of there's a big change in the mean. And I took this example straight from Jewel et al. And here they go out and they say, okay, well, what's the cost function of putting a change point, that is basically having a special covariate that would say there's a change point at observation, you know, next as you're coming through. And here they're saying, okay, what would that be at different points as you came through that data set? And so they've said, okay, if I only had the first 200 observations, what's the chance I'd say there's one there? It's probably pretty good. Versus as I get to more and more data, closer to 300 total observations, no, I don't think there's one out there in this latter period. But I think that cost function is most likely minimized right here around 200. It's not out here, you know, between 250 and 300. It's most likely there's a change point in the data right around 200. Right, and so it colors that in here as that overall cost function. So what you can do is around, if I can do this cost function around any one point, I basically can have 300 of these cost functions. And then I can look across all of them and say, okay, looking across all of those cheaply computed cost functions, where should I put the change points? And jointly make that determination because I can see the relative costs and benefits of putting them in all the points. Again, though, that's these big discrete changes. Let me finish with one last example where this gets a little more complicated. I'm still kind of toying with this example and the best way to present it. Here I've said, okay, there's a dynamic model where the data depend on their most recent values. So yt minus 1, yt minus 2, right? So it's 0.9 yt minus 1, minus 0.3 yt minus 2. And then I have this variable that describes the change point. And it's going to be distributed uniform between -0.5 and 0.5 for the middle chunk of observations, for observations 334 to 666. So Carl, this one also gets to your earlier thing of, well, how much data do you need to actually do this? Right? And this to me is a more realistic example, which is I have a window in which I believe there could have been a change point. I'm not real sure where it is, but I know somewhere it's in this realm of observations. And I'd like to know, if I apply these different things, is there a chance I'll find one in there? Now, remember what's going to happen. The one set of models, because they're only focused on the type 1 errors, are going to run the risk of understating change points, right? That's what the binary segmentation is going to do, right? Which is, in a sense, what was already discovered in saying, well, you don't find any change points out there in the most recent data for industrial production because, well, that's where the model's biased towards because of how that model's set up. Alternatively, the lasso is going to find lots of them. And it's probably going to overstate that there's change points in that interval between observations 334 and 666. Then we're going to have to prune those down somehow. And that's what the latest literature is trying to do, is to say, okay, if I find a lot of them, how do I prune down and find the most likely ones? Well, you probably should have a cost function for that. And the nice thing is what I had on the last slide shows you, you can get those cost functions. And the great thing is kind of a policy analyst or, you know, applied person doing this for somebody is you can take those in and show the decision maker and say, look, what's your cost function? How big of a change do you want me to have to illustrate to you? At what cost to be able to say the data changed or the data didn't change? So here's the data and change points. And it's really subtle, right? The one on the left is the actual plot of the data and the known change points. And if I take those two vertical red lines out of there, you really can't tell there's anything in there unless you're a really expert time series analyst. You won't look at that one on the far left and go, oh, there's something different in the middle. You know, this is where I always say there's the black art to doing time series analysis, to look at that and go, there's something going on there. So if I do the binary segmentation, it tends to find something near the first change point, right? Notice this cluster of them just before 400. But it kind of misses the ones out there later, and it finds some aberrant ones at the beginning and end. Well, that fits the overall pattern that I would expect from that. The lasso one really overfinds the number of change points, right? Because it's constantly going, I'm worried about a type 1 error. Oops, I'm worried about a type 2 error. I'm worried about a type 1. I'm worried about a type 2. So what does it do? It tends to give me way more change points, right? Which is great, but then it requires what Carl was suggesting, which is I got to have a lot of data, because now I got to cut through those and go, are these ones in here really likely near each other? And which ones are just noisy? So as you see there on the far right, there's a whole bunch of them that are suggested there. Right? Well, that's a lot more like real world data than this little toy example that Jewel and the rest of them give you. So if I go through and do that, you'll find, depending on which way I do that, if I'm just minimizing that cost function, that's going to determine how many and where I actually find those change points. And you'll see, the ones that have the lower probabilities are the ones that are more likely to be the change points. Well, if I discount the ones that are early on, because there's not a whole lot of data, it's not till I get to this one out here at like 340 that I start thinking, okay, yeah, maybe that one's distinctive relative to the other ones. Okay. So as a last thing, I can extend this. We can do multivariate versions of it really simply in a way that isn't there with the other techniques. So I can stack this up, and this is part of another project I've been doing, where we can take that whole lasso approach and extend it and look at, say, more than one time series at a time, where there may not be a clear alignment that there's a change point in all the time series I have at once. It could be in one of them, and then it's affecting the other ones. So this last example I have looks at this same thing with this later model by Safakani and his co-authors. And it builds on what I was showing you, which is these models are going to find a lot of candidate change points that then have to be pruned back in some way, right? You've got to go and compare those cost functions to locally screen out or combine which ones have to go together. And this is really where this literature is headed right now, is the approach that Jewel and co-authors there have found is we can find a lot of change points, but we don't really have a way to pick among them. What Safakani and his co-authors have come to is, no, there are some interesting ways to cut through this. How do I know they're onto something? Safakani's graduate student on this, Peng Bai, just got a job working for BlackRock. So you don't go to work for one of the top hedge funds in the world unless you're onto something. So he convinced somebody he's onto something. So I'm like, okay, I'm gonna look into this one some more. The nice thing then is you can do this, and it works well for data sets even when you have a whole bunch of time series relative to the data, right? So P is the number of time series. P can be, at or not far away from T, the total sample size here, Carl, and these work pretty well still.
Yeah.
What's interesting, though, is they pull out different patterns, right? So here I am trying to say, well, are there economic factors that are driving public opinion in the United States, right? So here I've plotted out presidential approval and partisan identification. And this model will go through and estimate the change points I mark out in magenta there in the right plot. For those with some background in economics, the gray highlighted regions are the National Bureau of Economic Research declared recessions in the United States. You'll notice none of them line up with when we see changes in the political variables. Which is kind of contrary to a lot of things you'd expect from analysis of public opinion, Carl. You'd think those would line up a little better. And I'd note that, there's very little of them lining up with the most recent, kind of more volatile political things. Let me close with one last one here, which is what happens when I do this for a bigger model where I include a whole bunch of other economic variables. Those are the ones kind of in light gray in here. And I point out, they don't really line up. They don't line up with major political events. They don't line up with elections. I've kind of speculated what they might be here at the bottom, but they're not really change points that we would say are kind of the critical ones from a political science or public policy perspective. All right, so I've got a whole Bayesian thing here on this as well, but in the interest of time, I'm going to leave time for questions. Mm-hmm. Let me give some final thoughts on these. One is, when are you doing this? Or when are you putting the time in on this? And usually it's because you're not sure of the timing or the structural change. That is, you don't know when and whether to specify the intervention variable. You're going to need some kind of model for this, or for the shift in the parameters, or some check on parameter constancy. We tend to like to think, oh, the past is some way predictive of sorry, I somehow got muted there.
Okay.
We like to think
I
that
thought it's my problem. Yeah.
No, it's mine. We tend to think that those past values are some way predictive, but really what can happen is we just get into saying it's the same process and don't want to admit the process changes. Well, a lot of times that happens, and it's indicative when you're trying to predict or you're trying to engage in causal inference, and you find out your prediction or your inference breaks down. Is very often it's something structurally changed in your data, or the way it was measured, or something else. Further, and this may come more from my experience in political science, but I'm really convinced at this point that most things in public policy, not necessarily in economics, but most things in public policy are actually variables that are stationary. And when we find evidence of those variables being non-stationary, it's either because we didn't measure something right, or we didn't account for a structural change. And the more interesting story is to account for the structural change about what it was that was different from the past to what we have today. Lastly, I've kind of given you 3 or 4 different approaches to this here. A lot of this comes down to computational cost. That's been the real driving thing in this. When you go back through those reviews of the literature and the development of the techniques and the rest, the reason that Safakani and their other co-authors are developing the stuff they're doing is basically driven by applications in engineering, where they have a whole bunch of interrelated time series. It could be network traffic, it could be COVID data, it could be just some kind of big data, and they need to find the breaks or the anomalies in it. And they need to do it quickly. And so in those situations, they need fast algorithms for doing this. And so what's really interesting there is some of the really cutting edge stuff in that is not coming out of economics. It's barely touching statistics. It's coming straight through from computer science and engineering and signal processing. So if you look here, here's kind of my last slide on this, which are just some different references and things to follow up on. Some of these are social science things, but other ones are coming straight out of statistics or signal processing, and they're really quite diverse in terms of where they're coming from and who's working on these problems and the rest. So it's been kind of a pleasure to have a chance to share some of this. I don't know what questions I've kicked off, but I've hopefully given you a good summary.
I have a few.
You have a few, okay.
Particularly on the P, but I will talk about that. And so let's check with, Christina has a question, and she's my data science class. In my example, the dependent variable is multi-family rental housing units produced through low-income housing tax credits that are on the ground. The units are a function of tax law changes, interest rate changes, national economy, local economy, housing law changes, implementation phase of laws, and construction timeframes, lease up timeframes, federal budgets. For sub-counties, model be a good one to use. Looks like you have a lot of P. Seems like a good candidate for doing the P larger than M, larger than T. Yeah.
My only question there, Carl, just from the description is it a segmented market, meaning it's segmented geographically? So it's like time series in states, time series in cities. Because there is some literature.
Could you, yeah. So how the dependent variable looks like? This is for the whole country, or over a long period of time, and dated back to maybe 1940s, and so how the can you give a little more detail about the dependent variable?
Carl,
Yeah, you can mute yourself, Christina.
It says since 86, if I'm reading the thing right.
Yeah, since 1986, looks like this.
Can she unmute herself, Carl?
Yeah, looks like
she's calling it. Yeah, she's.
Yeah. Oh, because she's doing multiple computers. So one is only for the video, one is only for the voice.
There is a literature that's come up on some of this stuff in panel data, and I could probably run that down and get you the site on it, Carl. But I know that like it's come out of the group that studied under Sid Chib at WashU. So it's probably like Young-Hee Park and Jun Pang at Tsinghua and that group of Sid Chib students in political science and economics. But if I remember, there's probably some people out of that group. The thing with that, though, is it's probably fully Bayesian. And I just wonder what the computational cost is on that for that. And I'd have to dig further back into those reviews. I'm trying to remember. I don't recall on these overview ones here. Yeah, the Allen and Horvath one is almost pure time series. The Joule topology that I've given you here is also pretty much pure time series, or kind of this glorified grouped means setup. But I could see doing it that way, though, because it would have a variable selection criteria. If you did have it pooled over the whole country, but you had it really disaggregated, because I mean, the housing sales data, typically you'd have monthly at a minimum, if not weekly. So you'd actually have a fair amount of data. I don't know the levels of aggregation and some of the other things. But there's definitely some things to look at there on that.
But I really think that regularization method could be better applied in this case, because
because the great thing with the regularization method there then is, if you're implementing those, is there's really well developed algorithms for those regularizations in both Python and in R. I mean, like when I look at the package, when I look at the packages that are built for doing this stuff in time series analysis in R, they're all just built right on top of the standard GLMNet framework for ElasticNet and Lasso models. I mean, so there's all it is,
Yeah.
all those packages are special wrappers to like deal with the data classes and the data types.
Yeah.
And set them up into the right stacked up regressions, and then they just dump them in to the standard GLMNet and ElasticNet models. Because those are really well developed and well done at this point.
Yeah.
So I think that's definitely
implementable.
doable.
Yeah. Yeah. And Christine also added that the time frames are layered on top of each other. I think this is, yeah, it makes sense. And I would not see something go down quick.
Yeah.
All of a sudden, and yeah. You see that it's a going layer, and yeah. So let's come back to this a little bit, and let me go to Raku's question. Penalties for lasso decided based on prior knowledge about the subject. Now, this is something I want you to elaborate more. How much that the prior or now, and you may need and not talk about the Bayesian part.
No, actually, I've thought about this a lot, because when you read, because I've dealt with having priors on these things in what I call the model type 3 here that I didn't really get into for this. And there is a literature there that looks at, well, what would those prior beliefs be about the number of change points? How much of that is derived from the data versus what happens if the data suggests a lot of change points really different than the prior. And I've done that kind of stuff. And usually your data is usually decent enough. The prior doesn't matter that much, at least in the applications of that I've done. Now on the lasso related stuff, there's actually, let me jump to that slide here. So on this, the penalty terms that you have to decide are what are the values of lambda 1 and what are the values of lambda 2. Now, in the setup that Safakani and his co-authors have, and the papers are incredibly detailed in this, they do all kinds of asymptotic math. They basically derive out for you the limiting values of the penalties, because they depend on the number of change points, the number of regressors, P, and the sample size, T. And they're scaled relative to some overall scale factor, call it C. So they're usually some scale factor of C times the square root of some weighted function of the logarithm of the number of parameters divided by the sample size. And that sets kind of the outer bound for what those lasso penalties have to be. And so the nice thing they did was when they wrote the software for it, you basically give it a ladder of values. And this is a real common Bayesian approach, actually, but they just implemented it as kind of a quasi-Bayesian or just, parameter searching strategy, where you give it basically a ladder of values. But it's a funny ladder. It's not a ladder like you're used to climbing on where the step heights are all the same. What happens is some of the step heights are really close to each other and some of the step heights are really far from each other. And so you try out what those are, and you basically have the limiting step value on one end of the ladder is the one that is suggested by what happens as the sample size gets big, what happens as the number of covariates gets big. And then the one on the other end is just kind of, I have no idea. And I've worked with that sum on those models, and it doesn't really seem to matter. It may change ever so slightly, like where exactly it says the change point is, but it usually doesn't change the number of them. So it may move a change point. Like if I think of this plot here, it may move where those magenta lines are, 5 observations one way or 5 observations another, but it's going to get for you within a window there. There's probably a change point around those dates. And that's usually, for most of what you're doing here, good enough. Now, there is a step to be played further in the Safakani approach, which is you would have to nail that down a little bit more if you're going to try and put confidence intervals around those change points.
All right, let me open up to any to the audience. Any questions from the Taiwan side first, maybe? Yeah. So far, we have been taking a lot of time in posing questions from US side. Peter, do you have any? You can ask any questions, and then or from any of these types. Doesn't have to be to the later types. I think is more interesting and.
Yeah. And let me try to interpret a couple of questions here. All right, and this one. Well, yeah, first of all, thank you, Dr. Brandt, for this wonderful talk. And about the final slides, you talked about when to use these models, right? And then could you just briefly recap a little bit, and then what are the cons of using? Well, you haven't talked about much about that, the Bayesian part, right? The model, the type 4. But I mean, the question, I'm not sure. It says about the Bayesian and the Gaussian model, and which one might have some advantage over the other in what conditions? Yeah.
So let me do one versus the other, and then the overall pros and cons. You know, if all I care about is I just want to get that I just need to split the sample, and I'm pretty sure the process is going to have stayed the same after a given break, then I'm probably in that world where the binary segmentation works pretty well. It's when I think things are really going to be different, or it's really sensitive to that I need something where I get that other approach, like what I get from the fused lasso stuff. Now, I think the fused lasso thing right now is kind of the hot thing to do because, well, it's just become what can be done right now. And there aren't that many papers that compare across those. So I think right now, still part of it's computational cost in picking one versus the other. In those. And I think that because that's still there in the papers, there's still always this discussion in the footnotes or in, you know, the supplemental materials or something about how long it takes to do this, you know, and get the right answer.
Okay.
Overall cons against it are, in some ways, it makes it where you don't have to then think about, well, what is it that's changing in the data? Because you could just come in here and say, well, I know something's changed. I gathered a bunch of data. I'm going to run it through here. And if I find a change, I'm going to put a label on it and call it a change and try and publish that, or try and convince my funders or whatever that something changed and we should study what changed, or we should do more of whatever happened around when that changed. And that's not really good either, because you've got to have some idea when to expect those. And so I think the con is it makes it really easy to say, I'm just going to let the data tell me, and I don't want to have to theorize about it, or I don't want to theorize about alternatives. I think that's bad. The Bayesian one that I didn't show, what's nice in that one is we're looking at basically terrorist kidnapping and targeting decisions. And we have really good ideas in those examples when we would expect to see changes in those variables. When we're looking at international, say, skyjackings, like we know, oh, hey, when we finally put metal detectors in all the airports, guess what? The number of skyjackings goes down because it makes it a lot harder to take over planes. So that's one we expect to see, and we see it there. So it adds some face validity to the model then in that. So then, at least when we see ones we didn't expect to see, it makes us think harder about whether that's more or less like the ones we already expected.
Okay. Okay.
Any more questions from
Mhm.
Taiwan side, US side, and
I got this one. Well, yeah, maybe. It says, but do you have any suggestions on getting a Python library for change point detection? Yeah, but maybe if you do, you can just type it or give it to Carl or something, or you can just say it right
Well,
now.
I can say this, which is at least if you were trying to implement the Safakani stuff and I wanted to do it in Python, I mean, if I were really wedded to having to do it in Python, there's two things I'd probably do to set that up and do it. One would be the underlying code that they call and compile to fit those models for the Safakani approach is actually all written in C and C++. And so what you should be able to do is write a wrapper to compile that and be able to pass your data over from Python to the compiled C code and be able to do it that way, just like you would do in R, just like you could do in MATLAB, any of those things. The other way to cheat and do it, if you haven't seen this, is there's an R package called Reticulate.
Okay.
Yeah.
And if you know what a reticulating Python is, you'll get the back reference on this. The Reticulate package allows you to basically do things from R and Python and from Python and R.
Okay.
And so that would be the other way to go about it. If you were mainly working on a Python side, you basically could have a version of R with Reticulate, set your data, do your stuff in Python, hand it over to R, get what you wanted back, and keep going in Python.
Okay. Yeah, one of the other students says about ruptures. Have you heard about that? It's just library. It's a Python library. Yeah. Okay.
It does. Okay.
All right, Carl. Do you have any other questions from your side?
Yeah.
Yourself.
I do not have anyone on the checkbox. I have one question though. I have quite a number of questions. First of all, it's classic. I think this is really, really, really cool. And for this survey of all these change point models, I think the way you categorize this is really, really, really interesting. It's epic. And I'm thinking about you cite a couple of examples, for example, that you can see the policy changes. So similarly, and also the seatbelt and the metal detector, they are. I'm thinking that those variables could be generally simpler or less complex compared to the last set of models. And if you can show the slides about the macro polity, and so I'm thinking about this. So, for example, one policy can see changes or how much, to what extent this phenomenon could be changed or could be circumvented. But in this case, so in the micropolity model, so this variable begs for a larger number of p's. So, for example, in this case, you clearly see that the partisanship didn't align well, and you can look at the differences of this partisanship and how one party, for example, the predominant Democrat period from 1960 to 1980, and versus a weak GOP, would that make a difference? And there could be some more piece here, and I'm thinking about it. This is, I mean, Lasso is a good direction, but it's still begging for really large number of pieces. Then you can see they can do the regularization better. And if you have, for example, two or three of them, or the two or three of them may not be big drivers, and you can also think about over time, and there could be more variables coming into picture, and the president and the party and all this. So how do you tackle different types?
There's a couple of things behind this. This is actually a whole nother talk I have. You're getting a snippet of a much bigger, probably hour-long talk on this one. This
So
already has in it, I mean,
bring it back.
those little gray series that are hiding in here, there's 6 of those plus the 4 here. So this is already like, you know, a 10 series model of monthly data from the 1950s, basically through, I can do it through like last month if I want. The presidential approval, which is in black, has been scaled so that it's done in deviations from its long run mean accounting for party. Right. So we've done like a party specific mean effect that's there so that, you know, basically when we talk about a 1 standard deviation change in one direction, it's different than a 1 standard deviation change the other direction. Right. One's a pro-democratic, the other one's pro-Republican, which is why you get kind of the valence flipping that's going on there. And that captures that part. Now, what isn't there, there's nothing about Congress there. So there's nothing about legislative polarization. The problem with legislative polarization or control of Congress is the variable, in a sense, is fixed every 2 years. So it's on a different time scale than these. It's very much the problem that your student was having before. That's another paper I actually just started working on this week, is how do I deal with the fact I have the differing time scales. And so what I want to do there is I want to figure out, how do I do these change point models, multivariate, but also account for the changes in the time scale? So I see my colleague, economist Vic, on here. So Vic, this is going to be, I want to do vector autoregressions with multiple imputation MIDAS setups with change points. Yeah, Vic's like, yeah, no, thank you. Yeah, I get it. Yeah. What's interesting though, Carl, to your point, is the other slide that I didn't show, which is I've gone through and taken and drawn out a version of the Gaussian graphic model that goes with each one of these regime periods. And it's the next slide. I didn't show it to you guys during the talk. So what this does is you get a little clustering and you get a little clustering for each one. And you'll see the variables are labeled with little circles. And so you have, CPI for inflation, FFR for the federal funds rate, GDP is GDP growth, M2 for the money supply, U for unemployment, CSCI is the consumer confidence index, commodity price growth is out there. So those have all been transferred to be stationary. The blue are the proportion of people who say they're Democrats. The red are the proportion who say they're Republicans. The green dot is the proportion who say they're independents. And the cyan, bluishy, greenish dot is presidential approval. Notice on all the top 6 plots, so the ones that cover January 61 through the end of the second Bush administration, January 2004. The party ones are all in the middle. The economic ones and approval are all on the outside. So just in terms of like basic causal inference, you're saying, okay, this constellation of economic factors and what presidents are doing or what we think of them is driving whether or not we're saying we're Democrats, Republicans, independents in the aggregate. Yeah. And it's a very consistent, so it fits your thing, Carl. It's this very consistent long pattern of what it means to be a Democrat or Republican or an independent in the aggregate over the entire period over which we measure those things in the United States consistently. Right? So from the beginning of time of modern survey research in the United States, the 50s, up through the early 2000s, things look pretty much the same. Then you hit that period after George W. Bush is reelected in 2004. Right? And this is just before that, but this is like right when Bush declares he's going to run for the second term. And things totally change. Those bottom 3 plots have causal graphs that look completely different.
That is Obama. Do you say?
It's the end of Bush. It's the end of Bush. It's Bush's second term. It's W's second term, Obama, Trump, and now
Obama.
Biden.
Yeah. Mm-hmm. Well,
And
2 years
those
later,
relationships are
3 years
just
later.
different.
Yeah.
It's 3 presidencies.
Yeah, this is super interesting. This is super interesting for this beginning 2010 January. Yeah. I think this is another talk. This is another big talk.
It is
Yeah,
another
we're gonna
whole
talk
paper.
about this.
Yeah, it is another whole paper. Yes, and I know that one I was supposed to present this past Monday, but we had job candidates on campus. That's why you didn't get to see that one on Monday.
My goodness, we are fortunate to get this debut here at the Colloquium. Victor, have a hand up. Sorry, I take too much.
He's
Victor,
probably going
please
to
go
tell
ahead.
me the economy changed.
Yeah, right. No. So sorry, I had to switch. Sorry about the comment earlier. I was crunching, and so it's in a computer that I don't have a mic or a camera. So this was so fun that I wanted to come and talk to you. First of all, I really want to talk to you about this, because the Judea Pearl type causality graphs in VARs has somewhat been abandoned in macro, and Lutz Killian has a big critique of it, and I'm not convinced about the critique. So I really want to learn from you. I want to talk to you about this.
So this paper, the paper I'm pulling this out of, just came out.
Great. But
I'll send you the site.
And I'd love to talk to you. I have a different question, kind of more philosophical, and sorry to bring you back to Bayesian, but that's, you kind of ended there, and that's where your expertise is. So I kind of have this question too. When I'm thinking, I'm not thinking about a structural change with a known point. So it's not the Chow-Tai test or something like that. I'm thinking when you started, Biden Perron. There is all these papers in the 90s by Andrew. So basically, Andrews wrote a paper a year in Econometrica about a structural change. So, and so these kind
he wrote one paper that he could cite himself in 10 times.
Yeah, right. That's how Econometrica works. So, I mean, it's kind of philosophical, so I just want to get your sense of it because I have no idea about this. So if I'm thinking about looking for a structural break, and it's structural at a non-period, but I want to apply some causality to it, or I want to kind of have some sense of causality of that break. Philosophically speaking, from a Bayesian perspective, if you're appending like a probability mass and a diffusion to that, are you then considering that this structural causal kind of break is kind of a random variable? And in that case, doesn't that kind of violate kind of the concept of what a structural break is? And so I wonder if, again, love to learn more from you about this. So I'll come back in the office. I wonder if the Bayesian approach would be more tractable for finding incidents of breaks. So if I have a big sample, I may kind of approach it as there is kind of a random chance that there is a number of breaks that I don't know about, and I'm gonna apply priors to that, but I'm not going to go ahead and go to that extra step of applying a prior on a structural break that has some causal aspect to it, because that's basically kind of looking for what I want. I know it's a broad question, but you're the expert there. Do you have a sense that philosophically speaking, because all this structural break stuff has been largely frequentist, right? And then when you go to Bayesian, then you do time varying parameter, and then let everything go. And so, do you get a sense that this could be tractable? From a philosophical perspective of I'm looking for a structural break, I'm gonna, I have some prior on it, but I'm also trying to kind of get to the cause. So I'm not looking for outliers or something like that. I'm looking for like a cause of this. Is there kind of something to that?
So it would be like in some of those elastic net models that I think of from like epidemiology and stuff, where you say, okay, I have a whole bunch of features that predict whether or not you have a disease, right? But I don't know which additional markers or things I need to include. But I know I've got to include these 5 things, right? In other words, I have to include your basic 5 vital signs. You know, I have to differentiate for gender. I have to differentiate for age. I have to differentiate for respiration, pulse, you know, blood glucose. And then what's the next marker I need to be predictive? Well, I don't know. It's going to depend on picking among this big set, but I know that subset has to be there, right? So this is kind of the argument in, and there's a little bit of this in the Safakani stuff where they've gone through and taken kind of what Venura and some of these other macro people have done, where they've said, I have this really big set of covariates. I want to whittle back through them, and I know maybe there's some I pretty much always have to have in the model. But it runs up against this thing that Jewell and Fernhead and their co-authors are doing, which is like, okay, right as I get right up to the point where I think there could be a change point, and notice I think, I don't know for sure, it's always I think, the distribution changes. Something about the distribution changes, meaning if I'm in the neighborhood of the change point, the data in the neighborhood of the change point are somehow not like the data prior, and they're not like the data that come after. So there's something you have to say of, they're not really part of the IID group. So forget all the time series, forget all the dynamics. They're just not like the IID ones on this side, and they're not really like the IID ones on that side. So I don't know which one, and I'm always trying to figure it out. So that gets a lot tougher to think through, like what's the easy way out of that. And I always thought it was kind of this dynamic specification. I got to get the time series model right. And then I started reading through the Jewell paper, and I'm like, why are they just talking about changing in the mean indexed by time? And then I thought about it, and they laid out some examples, and I'm like, oh, this is actually a lot harder than I thought. That's why I did that example that's in here, like this one, where I said, let the intervention be a random walk, right? Because I basically played with it. Here, the random walk has no drift and has no memory. But I put it together in such a way where you could have, in this period in between, you could have a random walk. You know, so you go from a stationary period or a random walk period back to a stationary period, or vice versa. We could probably stand around dry erase boards for hours at that point.
Yeah.
But,
fractional integration, right? Fractional integration. Yeah.
But I come back to, like, when we do the Bayesian ones, computationally, if you want your way out of it, the way the Bayesian approach says to do is what's in this slide, which is I got to do the reversible jump thing, which is, okay, you could do everything time varies. So every time period, I add a new observation, I update the regression. I add another time period, I update the regression. So basically, just as I get a whole set of my time series, I get a whole set of vectors of the regression effects all the way through. Or I can limit that down and say, well, what could happen? I could have a change point. Well, great. Now I need a probabilistic space in which the change points occur. And this is what you have to buy into for the structure of that to make that work from Peter Green's work, right? Is the reversible jump setup, right? I have a new level of the data. I reverted back a death step. One is I keep the change point, but I change its likelihood. Or I keep the same change point, but I slide it. And the way I always think about this is you have a hill and you have to build the closest set of stairs you can build to that hill. And so you're facing the time every time you go to take the next step. Do I need to build a new tread? Do I extend? Am I already on the level and I have to stay on that one? Do I rip the whole step out because what I already started building was the wrong step? Or did I have the right step? I just got to slide it forward or backwards from wherever I had it now. And now once you realize that, you're like, oh, that's why stairs cost so much when I have them installed in the house.
Do the elevator. All right. Thank you, Victor, and excellent question. And I wish I have more time. Christina has a follow-up comments, a question. She asked, what factors should be in the former question that she, example she cited before, and what factors should be considered with the confidence interval calculations when the time frame of each of variables are disparate. And I think she meant that these variables are very different time frame. Yeah. Do you consistently?
This is where I probably would need, because the stuff that they published on this doesn't really cover that. I can't imagine they didn't work it out though, because one of the co-authors on that stuff in this statistics group down at Florida, the guy wrote a whole dissertation on it. This is the guy who got the job at BlackRock. And I can't imagine the statisticians let him get through without putting some approximate confidence interval on these things. You know, an economist would let you through by just saying, well, you can consistently estimate it. I don't have to worry about a standard error on it. You know, consistency will be enough, but I would think the statistician would have wanted the standard error or some sort of credible interval on it. But I'd have to dig back through that dissertation, and I know I have a copy of it. I'm remembering the structure of it, and it's probably in what I think would be the end of chapter 3 or maybe chapter 4 of that student's dissertation. But I don't think they published it yet, if it is there. But I have that citation, so I can pull that and get it. I don't know that the predictability is that hard. You can make the prediction. It's just, it makes it hard to say, is this change point different than one that's really close to it? Right, because you can always go through and say, okay, well, if I've subsampled the data around a change point or a region of change points, push the data to either side and say, what's the regression on this side? What's the regression on that side? And in that sense, we know how to work with that problem. The real problem is when you're right in around the edge, because where you classify those ones right in at the edge is what's really going to change what you say about those confidence intervals. I mean, that's the one thing out of this literature is you really are worried about the edge. And that's Vic's earlier comment of what happens when you add the pandemic in to like the industrial production. It really changes where you thought the edges were on everything.
All right. Okay. I want to check with Peter again. Any question from the Taiwan side? I promise, and we have to wrap at 11:55. So because we have another event the other side, so we have a couple more minutes. And Peter, can we accommodate one last question?
Yeah, not from here.
You want to conclude?
Yeah.
Okay.
We don't have any more questions here.
All right. I think I would like to conclude here. Allow me to conclude a few minutes earlier because on the Taiwan side, they have another function next door. Peter has to attend that to conclude that, give a concluding remark. And so this is really really a data rich and a very super interesting. I think a lot. I wish I had more time to see you to do that GGM model and all those graphic models. So maybe we should invite you again back, and then maybe in the next season, and we'll hope that we can and have more Bayesian works, and I think because of interest of time, we did not have a chance to present more detail. And thank you very much again, Peter, and Patrick, and yeah, such an excellent talk. And so we will post the recording on our website, and for those who want to revisit, and please check our website, and also Dr. Brandt will send me the slides, and so we can post the slides too. So and allow us to give Dr. Brandt a really big round of applause. We can do it virtually, and we'll do it. Thank you very much. Thank you, Peter.
Yeah,
Thanks, everybody.
Thank you,
It's been a pleasure.
Yes.
Okay.
Thank you. Thank you very
Thank
much.
you. Thank
Yeah,
you.
it's very enlightening and fun. Thank you.
Thank you for the audience too, and Victor and another economic professors are coming. And we have one last episode, our last event, which will be December 1st. Please stay tuned, and we will talk about that. We get our correspondence and get back to us on December 1st, the last colloquium, and by econometrician, and from Cornell, his name is Chen Chi, and so that will be the last one of this year. Thank you again. Okay.
Yeah.
All right.
You all have a good night and a good
Yep, you too.
good day
Yes.
in Taiwan.
Thank you.
Thank you. Thank you all.
Bye, everyone.
Thank you.
Thank you.
Thank you. Thank you. Bye.